Good day. For the Robot Dynamics course project, myself, Gregory Jones, and Nathaniel Bernal are doing or have done the reinforcement learning for motion planning of a robot arm project, and we'll be going through all the details. The main goal of the task or the problem that we wanted to solve was moving the end effector of the robot arm to a goal position as quickly as possible, only taking into consideration the actual position and not the orientation. Now, traditional methods have used typically use some kind of motion planning and or trajectory generation, which then generates a motion that is then fed into a robot controller. However, in our case, we've used reinforcement learning, which is a more modern approach that's common in literature or advanced literature. So, um, generally, how reinforcement learning works, if you take a look at the diagram at the top right, there's an agent or policy that interacts with an environment through trial and error in order to maximize the long-term accumulated reward that's returned by the environment. How it does that is the agent or policy applies a specific action to the environment. The environment is stepped forward by one time step and then returns a next state as well as the reward. The return is defined as an infinite sequence of these reward interactions. And one of the main underlying assumptions with reinforcement learning is that the environment is modeled as a Markov decision process, which you can see here is a probability distribution based on the current state and the action applied from that state to the environment. And then the generated reward would be stochastic as well as the next state. And we actually ended up using an algorithm which is model free and doesn't require an explicit model. And so that was quite helpful. And then the policy itself generally can be stochastic, which helps with exploration and learning the different states and possible rewards. And the policy tries to maximize what's called the state value function, and that's defined below here. Essentially, it gives the value of a particular state, and that's represented as an expectation of the policy of the return from that state. Now, there are more advanced algorithms such as PPO or proximal policy optimization, which we used based on or that uses deep reinforcement learning. We don't go over the details of that, but we wanted to include this slide to give you some intuition. So the other thing that we looked at was the how changing the dynamics of the robot arm would affect the policy. And so in order to understand the intuition of that, it's important to keep in mind this dynamics equation, which uses the mass matrix, Coriolis matrix, and a gravity term, and that's related to the joint torque vector. And this mass matrix term actually depends on the mass of each link as well as the inertia of each link. And then the gravity term also through the total potential energy expression depends on the mass of each link too. Now, a lot of the work that we put in involved creating the environment, which we did using Gymnasium. And we trained the PPO policy or algorithm using stable baseline 3 with an existing implementation. And the environment that we used depended on Majoko, the simulator, which simulated the dynamics of the robot arm, and that loaded a model of the arm through an XML file. Now, the general flow on the right-hand side, as you can see, is that an input action representing the relative position command was then converted into an absolute position joint vector, and each of those elements were applied to the joint position controllers, and that then fed into controlling the actual robot arm, The simulation was stepped forward by one time step, and then the reward and next state were calculated. In particular, the state was defined as the elements of the joint position vector, as well as the goal position in cylindrical coordinates, and that was normalized by dividing by a maximum value. And then the reward function was defined as this exponential using the distance between the goal and the end effector, which was maximum when this difference was zero, so that encouraged the policy to move the end effector towards the goal.
So training the policy meant repeatedly stepping through the reinforcement learning loop for roughly 4 million environment interactions, updating the PPO networks after every batch to keep the agent from overfitting for a small set of start states. The end effector and the goal were both reset to random, reachable positions at the beginning of each episode. From that state, the environment advanced exactly 300 steps. And after that point, the episode was truncated, not terminated. Truncation lets the algorithm assume the policy could continue to act in the same state later, so it still assigns value to the final observation, whereas a hard termination would force the future reward to estimate to zero. An earlier version of the code mistakenly used termination whenever a goal was reached, which encouraged the policy to hover just outside of the goal zone. So switching to truncation fixed that issue and immediately improved learning speed. Data collection was accelerated with 20 parallel simulation workers. A vectorized wrapper expanded the observation, action, and reward tensors across the worker dimension, merged the per worker trajectories into a single batch, and fed that batch into the PPO update, giving a nearly linear speed up without changing the algorithm itself. Creating random initial poses required a least squares inverse kinematic solver, and if the solver failed to converge within a set number of iterations, Gaussian noise was injected into the joint angles, and the solver tried again until a feasible pose was found. During training, the mean episode reward and episode length from each worker were aggregated and written to TensorBoard after every completed episode, then reset, so the next rollout started with fresh counters. Reward growth began to level off after roughly 4 million steps, so further training was stopped at that point. Next slide. So our evaluation results show that the PPO policy handled moderate changes to the arm's mass and inertia very well. For scale factors up to 2.3, total episode reward stayed essentially flat, indicating little to no performance loss. Once the robot became significantly heavier, at scale factors of 4.4 and 9, we finally saw meaningful drops in reward to about 140 and 250 respectively. This gradual decline reinforces earlier findings that PPO policies tend to taper off smoothly rather than fail abruptly when faced with moderate dynamic shifts. Next slide. So these figures express motion terms of the trajectories in both the scaled and unscaled cases. In the unscaled case, the end effector reaches the target in roughly 30 of the 300 available steps and converges to a position error of 0.007 meters. Under the 9 times load, it takes about 165 steps to arrive and stabilizes with a larger 0.095 meter error, clearly illustrating slower convergence. The root cause follows directly from the robot dynamics. Each joint configuration receives roughly the same desired position command and the same effective torque. Scaling every link linearly inflates the mass matrix and gravity vector. Larger inertia terms reduce joint acceleration, while the heavier gravity terms can eventually demand more torque than the motors can supply, slowing progress and in extreme cases, preventing the goal from being reached. Next slide. So this is a demonstration of the unscaled case. And as shown, the end effector moves to the goal very quickly, which was reflected in the trajectory plots. And as was stated before, there was no regard to the orientation, only the position. And next slide. And this is for the 9 times scaled case. And this evaluation shows just how far the end effector ends up from the goal in most cases. And this may not be as apparent when just looking at the trajectory plots. The robot is struggling to reach the goal. Okay, next slide.
So we were able to test the policy out on the hardware, and we didn't end up using any sim-to-real transfer. And you can see in this video, the robot displays some rapid oscillation at the goal position, and this behavior ended up causing the robot arm to collide with the table several times and resulted in one of the motors breaking. So we weren't able to do any further tests, but um, after that we were able to identify a model inaccuracy in the parameters used for the simulation for the model of the actuator. So we ended up correcting that. Um, and so that just kind of highlights the importance of the model inaccuracies as well as some sim-to-real transfer. So in summary, we were able to achieve the main goal of moving the end effector of the robot arm to arbitrary target positions as quickly as possible using a trained reinforcement learning policy within errors of 6 to 7 millimeters. And the policy was also robust to some moderate increases in the properties of the dynamics or the masses and inertias of the links. However, increasing it, these masses and inertias too high would affect the performance of the policy to the point where it wouldn't be able to reach the goal or would move to it very slowly. And then we're also able to identify the importance of using more formal sim-to-real transfer methods, as well as ensuring that the um, simulation model was somewhat accurate to the real model. Thank you.